So yeah, we're on. So let's get started. So welcome back, everyone. Thanks for joining in today. In this second part of this introductory interaction on modeling and simulation of engineering systems. My name is Praful. I work with the Mathworks in their Delhi office, and my role is involves primarily interacting with educators, researchers, students in their use of MATLAB and Simulink. So what I'll will be continuing from where we left off the day before. Again, to those of you who kind of are joining in as from for the second time. So I think in the previous interaction we talked primarily about uh, wireless communication and then the need for modeling and simulation in here. So we looked at a very basic example of how you could use MATLAB to model an analog modulation scheme, maybe publish that model as an app so that you can control parameters of the entire uh, uh, parameters of what you're programming, provide a GUI to kind of for others to interact with, to play around with, and then go ahead. Right. So again, how do circuits and where does circuit simulation sort of come in here, right? Uh, we'll talk a little bit more about that and hopefully kind of delve a little bit more. So again, as we took a brief poll last time, I think many of you are MATLAB users, but a very few of you might have used Simulink a little bit, Simscape maybe, and so on. And so I just want to kind of maybe talk a little bit more on that front as well. Okay. So again, I just take wireless as an example, but it can essentially be any area. But if you look at a typical wireless system, you would have, say, your baseband and front ends on the transmitter side, your mixed signal circuits, analog circuits for the antenna. You transmits the signal into the channel. At the other end, you kind of have the entire circuitry in reverse, the receiving antenna, your again, your low noise amplifiers, your A to D converters, and then again, your decoders and demodulators here, right? Again, it's a fairly complex system. So with and complexity is only increasing over time, right? So the idea is whenever you're designing, say, circuits for one part of this, you have to take the rest of the system into account. How does this design sort of fit into a larger scheme of things, right? And validate it across in the requirements which are there, right? And this is where different modeling approaches come into play. Very often we only model using code, but there are other modeling approaches such as using block diagrams, using circuit diagrams, or state charts, which can be quite powerful when coming across these when trying to model behavior of these systems. And this is where Simulink and MATLAB sort of come in, and modeling and simulation in general at various levels sort of come in, right? So a few things which I want to kind of point out is like very often we try to say MATLAB code or C code to kind of model something, or we would define, say, something in block diagrams and so on. And there are various libraries, toolboxes within MATLAB to do this. Instead of focusing on those details, the idea is today is just to kind of give you a general sense of what is possible, and the details of it is something that will only come as you explore tools like MATLAB and other simulation tools in your domain more and more. Okay. So that was about a wireless modeling tool. But since this is for the solid state circuit society, let's look at maybe ASIC design and maybe challenges which crop up here, right? So typically, you would look at uh, a set of specifications to start your modeling and to implement, right? And from your specifications, you'd again go into the implementation stage. So the analog designers would go look at their part of the specifications and look at modeling their circuits in SPICE. Similarly, you would have your digital designers going ahead and writing HDL code, and then maybe there would be software engineers who would look at maybe interfacing other embedded systems which are part of this larger picture, right? Uh, and then what ends up happening is each of these teams typically you would work in your own domain, and then you try to integrate it at the very end, where and try to bring together that entire system, right? So it's the same if you're working in maybe controls, robotics, any other area. There would be teams with different skill sets, which try to kind of uh, which are trying to kind of uh, more model and simulate, and we are trying to kind of and very often they work in silos. Okay. What ends up happening in that case is errors are typically found when you only go towards integration, right? Even if you are testing at each of these individual levels, each of the teams is carrying out tests on their own, you would end up with uh, when you test during integration, a lot of errors end up cropping up. Okay, this is because very often we are, our specs are very isolated from our verification itself. So specs often change. Sometimes specs themselves might be incomplete. You may have to kind of go back, add something to the specification and write. And this leads to kind of there isn't as much abstraction in the design. Also, it makes design trade-offs difficult. So each of the teams might be making design trade-offs when doing their own design, but at an overall level, it might be very difficult to sort of uh, do your design trade-off. Right? How is a trade-off that say uh, uh, analog design team sort of taking on, how does it affect the rest of the system? That often kind of isn't explored as much and is only found at the very later stage, right? And each of the tools are sort of disconnected. So every domain has their own specific tools. So the idea is not to stop using those tools, but use those tools in conjunction with others, right? Uh, and often design iterations slow down because of disconnection, these broken connections between teams, right? So naturally, if you look at where errors are introduced versus where they are detected, typically errors are introduced early on in the process and as you kind of go through the design, while they're only discovered at the later stage. And so the idea with modeling and simulation is to kind of find errors early and and account for them, make decisions so that by the time you kind of come towards integration, there isn't much error there. So this is what is called shift left verification. If you've come across, many of you might be already familiar with this. So and what it means is there's increased modeling and simulation at all levels, along with verification and validation as well. Okay, so we looked at, let's jump straight in. We looked at some how you could use MATLAB for some modeling, right? So now let's look at some Simulink and how you would use that to model. Okay. So to others, so what you can do is you can use an online version of MATLAB. So I'll post the link again from earlier. So this is an online browser-based version of MATLAB. which you can access. You can simply go ahead, click on this. If you attended the first one, I think you might have already created a Mathworks account and started working with it. And you can simply go ahead and try and use this. So this is running on this is connected to MATLAB running on our servers, on the Mathworks servers. So the speed at which this response is often determined by our internet connection speeds. So in case if this is slow, please try downloading a copy and then running it. Okay. Also, this online version is not really equivalent to the desktop version, I would say, but for the purpose of this interaction, I think it should work fine. Okay. So let's go ahead and jump right in. So I'll open up MATLAB and I'll get into Simulink. So yeah. So before I get into Simulink, right? So Simulink, let's talk a little bit about what MATLAB is and what Simulink is. How do they differ slightly, and uh, and then go from there. Okay. So suppose I have to just maybe create a simple simple sine wave, all right, in a script. Uh, so let's pick up where we left off that day. Let's try and create a simple sine wave. Go ahead and model this. So I'll just go ahead and define a time step. Okay, so let me just zoom this in a little bit. So I'll go ahead and define a time step. Say my time step is 1 millisecond. I'll go ahead and define a series of things. So a time points, say between 0 and 1 second in steps of t-step. So now if I simply run this particular section, so you'll see I get a variable t-step and I get array uh, 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 which goes from 0 in steps of 1 millisecond, right? Suppose now I have to plot a signal. So let me just go ahead and plot uh, a sine wave. So I have to create a sine wave. So say y is equal to sine 2 pi. Let me take a frequency which is similar to this. So let me just take a frequency as say 10, easier for visualization, and I'll just do it in 3 points. Okay. So if I go ahead, so this gives me y, and I can go ahead and plot this, right? So one way to plot that we saw that day was to simply go into MATLAB, select the two variables, y and time points, go to the plots tab and plot this, which gives me a plot like this. Or maybe let me just switch these two together, and it gives me a simple plot like this. Right? The other option, if especially when you're writing a script, is if you go into the editor, there is uh, there is a task here which can, let me just go ahead and magnify this a little bit as well. So yeah, so there is a task here called create plot. If I simply go there, it will just close this up. Yeah. So I simply click on the task and create plot, it gives me this task wherein I can go ahead and select the sort of plot that I want, and I can go ahead and then interactively plot. So this is useful typically when you don't know what sort of plots you want. So here I'll just go ahead and select this. So I'll just select X data as time points, Y is my signal, and I'll just go ahead and plot this. Okay. So the same thing, it in the background, it's the GUI is simply generating code. So if you click on this drop down, it's generating code. So if you select any other plot, you can go ahead and do that as well. Okay. Now, why am I doing this? So this is very simple. We're just generating a sine wave, right? But so think about what you had to do when you use MATLAB to generate this, right? So this is one thing that you're simply creating a time step. You're giving time points and then solving an expression. So this can be anything. This can be a simple sine wave plot, or it can be anything that maybe a solver that you've written for some simulation. Right? Now let's try and do this in Simulink. So Simulink is a block diagram based environment, which I mentioned earlier, right? So Simulink can be started right from here, and in Simulink, instead of writing code, you kind of model things using blocks. And so I'll just go ahead and create a blank model. And Simulink can be really powerful because it has an inbuilt sense of time, which makes it really powerful for dynamic simulations. Okay, so I'll again, if you see here, there is something called stop time here, and there is a blank screen. So now here, let me just go ahead and generate a sine wave here itself and highlight how things behave. So if I simply go to the library browser, okay, this opens up a browser which kind of has different blocks. So I can use, say, commonly used blocks, or so there are a bunch of blocks which you can drag and drop. So if I look at the source block, so I'll just go ahead and create, say, sine wave from here. I'll just drag and drop this inside. And I'll go ahead and create this. So there is a sine wave block which is there. If I double click on this, I get a bunch of block parameters such as its amplitude, frequency, and so on. So again, I'll keep the amplitude as 1, frequency as, say, 10. Again, this is in radians per second, but yeah. Some phase, some sample time. I'll just go ahead and apply this. Okay. In case you want to, this is simply a time-based sine wave, but if you want a sample-based sine wave, you could go ahead and select that as well. And now let's just go ahead and put in just view this sine wave. So if I go to the sinks section here, I'll find a scope which I can go ahead and plot as well. So if I just simply join the two, I can open this up and go ahead and run this. So the scope will open up a scope like block here, and it gives me some signal. Now this is obviously not the sine wave which I plotted, right? What's happening in the background is Simulink is there are a bunch of mathematical solvers which are going on which are defining a sine wave in the background and trying to solve this. Now, why is this? Obviously, let's go ahead and look at some of these options before then seeing how this is useful in the circuit design. Okay. So I'll just go ahead and look at some of these options. So let me just go ahead and look at the modeling tab and the model settings here. Okay. So inside model settings, there are a bunch of options which are available. So I hope this is visible. Yeah, so there are a bunch of options inside model settings. It says something like there's a simulation time, there's a start time, there's a stop time, it's a variable step solver, and so on. So if I look at the solver, it has some things. Right? So if I just change this to maybe a fixed step, and let me just go ahead and change this, apply this. What I can do is if I go back and rerun this, or let me just go ahead and define maybe a time step as well. Let's look at, say, 20 minus 3, the same time step that we had, right? So now if we go ahead and define this, this gives me more or less a sine wave here. So can you hear me? Can you maybe just confirm if you can hear me? I can see my video is stuck.
Yes, Praful, we can hear you.
Sure. Okay. I'll just switch off video. Just I think maybe I don't know what. Yeah. So yeah. So I think so. So what happened here? So what is the solver, and what happened when we did this, right? So essentially a variable step, a fixed step. So these are solvers. These are mathematical solvers which are trying to solve for this model that you end up building, and sort of try to kind of go ahead and build. Uh, so and so you can essentially model continuous time systems as well as discrete time systems using these, right? You can define, say, your time steps wherever you want to kind of compute different uh, values at different points in the model, and uh, essentially used to model this entire uh, system at a very high level. So how can you do that? So you could look at, say, uh, using mathematical operations to kind of go ahead and define what is happening, right? Or in cases where you looking at, say, communications, so you can go ahead and look at your say introducing different impairments, or introducing different sort of filters and so on and so forth. Right? So the same thing sort of applies across other domains, like say for your RF circuits. So you can go ahead and define different sort of elements and try to model this behavior. Right? And the best part is essentially, so think about if you're trying to keep track of time in a MATLAB program, or any programming language for that matter, versus if you want to keep track of time for in Simulink. So in Simulink, you can go ahead and since the sense of time here is inbuilt, it just simulated simply by me defining, dragging and dropping these two blocks and simulating this for the time being. So if I say simulate this instead of 10 seconds, if I simulate this for 20 seconds, okay, I can just go ahead and run this, and so my simulation now runs for 20. Okay, so I hope that sort of makes it clear. Now, uh, so so Simulink has an inbuilt sense of time. It can uh, models your different blocks, different components, and so on. Now let's look at come back to this, and look at like how we can go ahead and uh, look at some analog implementation or digital implementation here. So I'll quickly look at the digital one first. Okay. Now think of if you had, say, a filter, for example, which you had to build, and you had to implement that filter in an HTL code. You had to write HTL code for that filter. Okay. So one way you can do that is you can simply say, again, what I'll do is I'll maybe go ahead and start with the MATLAB environment again, because many of you were familiar with that. So if I go back to apps, so I think, and look at the filter. So there are a bunch of apps here, filter builder and filter designer. So I'll just open up the filter designer. And it gives me an option. So I want to design maybe a low pass filter. Okay, I want a low pass filter. Uh, uh, I'll use an FIR, whatever the equitable. I'll specify a minimum order. I'll just go ahead with the basic default options here. Okay, but you can see all of the things that you can modify, your pass band, stop band, and so on and so forth. And I'll just go ahead and design this filter. Okay, so this should give me the filter response here. So it gives me the response right here. If I want to analyze this in different forms, I could go ahead and look at my pole zero plots. I can go ahead and look at say, if I quantize this filter, right? How right now the filter might have, if I look at realizing the filter itself using basic blocks, or if I look at the filter coefficients itself, right? So the coefficients itself might be like double. So it might be in floating points, right? But maybe I want to kind of have a fixed point implementation. So I can simply go ahead and look at the fixed point implementation, and you can see the filter response changes a little bit, right? So we need to account for that, right? That's where fit modeling and all of that come in again. We again maybe want to examine other things such as say your interpolation and so on and so forth, or maybe examine other things such as say filter delays or any phase difference that filtering introduces, right? So after examining all of these things, we can simply go to implementation. Okay, so say if we want to go to Simulink, so I just can look at one of this particular implementation. I can go to create a block, okay, and maybe build it using basic elements. And I'll just go ahead and click on realize model. Okay, so we created a quick filter, examined say various properties, and then went ahead and quickly realized the model. And what that did was it created a filter block here. Let me just go back and do this. So it created a filter block here, which you can see gives me the implementation, right? So I tried to implement this using basic building blocks. So you have your delays, you have your uh, gain blocks and your addition blocks here, right? Now, and you can see how big this filter is, right? So now, if I want to say go from this particular filter block to uh, HTL code, right? So what do we do? So we could simply go ahead, select this particular block, or maybe a bunch of other blocks which we want to generate HTL code for. Maybe after the filter, there's maybe a bunch of other processing that you are doing, right? So maybe add those things. So what you can do is you can simply say, combine all of these things into a subsystem. So you can create a subsystem out of this. So inside the subsystem, okay, so and then for the subsystem itself, you can, if you simply right click, you can go ahead and look at generating code for these things. So for example, you can just simply go ahead and generate C code for this. So or you can generate HTML code for this. Okay. So if I click on go on HTML code, the easiest way to do this is you could simply look at something called the HTML workflow advisor. So an option. So one way of getting to this is simply right-clicking, go to HTML code, look at HTML workflow advisor. Or another way to get to the same place is again go to your app section and uh, look at a bunch of code generation apps which are available here. So you can simply go ahead and generate HTML code for that. Okay. So now what the HTML workflow advisor gives me is a bunch of options to sort of select my target device. Okay. So say I want to generate generic, I just want to generate some code. Okay. So you need to kind of, in this case, MATLAB sort of integrates with other synthesis tools. So in this case, those synthesis tools are maybe Xilinx Vivado. So for that, what you need to do is simply go ahead and provide this synthesis tool. So right now it's saying it doesn't find any tool available. So what we can do is we can simply go ahead and look at a function called HTML setup toolpath, and this will simply, or if you can just search for help on this, it will provide us with options for how to kind of do this. So you can set up your Intel Quartus or Quartus Pro or your Xilinx Vivado or ISE. Right? So it also works with say Microsemi and other vendors as well. So right now I'm just going to kind of go ahead and copy this. So this is just an example. So I'll just modify this for my own work here. And yeah, so let me see. I think I have Vivado. My version of Vivado is 2019.2. Let me just find this. See. So Xilinx Vivado. Yeah. Then yeah. So I think my version is 2020.2. So I'll just go ahead and do that. And the rest of it remains the same. I'll just, so right now it repends this. And what I'll do is again, I'll just close this again and I'll restart Workflow Advisor. So I'll just go ahead, get HTML code, HTML Workflow Advisor. Okay, so yeah. So now you can see I get the synthesis tool up here. All right, I can select which family to kind of target for my verification, and then we can go ahead and that as well. So I can simply go ahead, run through this entire task, and at the end get VHDL code for my filter. All right. So yeah. So what I'll do is I can let me just see if I can run it till so I can set my target frequency, set my HDL. So let me just maybe run this at 10 megahertz. I'll just check severity. There were some warnings. We can go ahead and check these, but yeah. And then we can look at HDL code generation. So you can either look at generating Verilog or VHDL code here. So you can go ahead and look at Verilog or VHDL. You can optimize code to a certain extent as well. You can look at pipelining, resource sharing to kind of reduce your reduce the amount of hardware that you use, um, or increase speed. Okay, reduce your critical path. So, and you have a bunch of other options which you could look at as well. So you can simply go ahead and say, hopefully this, and I can go ahead and generate my RTL, as well as if you want to generate a test bench, or you could go ahead and do that. So yeah. So here it will simply take its time. Sort of it's so MATLAB will work with Vivado to kind of generate code, and now can see it has generated an okay. Unfortunately, it has so it has generated some HDL code along with my VHDL files and so on. Okay. So this is something which was generated just now. If let me just go ahead and open this. So yeah, so it kind of went ahead and generated this. Let's maybe have a look at the VHDL code itself. So you can see this is the VHDL code which was just generated, and it can it has a bunch of delays, multipliers, adders, and so on. Right. So this is, again, you can trace it back to the Simulink model. So which code generated what? So you could go ahead and look at the model, as well as you have traceability to look at what part of what code corresponds to what block, and so on and so forth. So that was one thing that you can do, right? So the idea is, again, how do we work with this? If you are designing, say, a system and which you want to implement on an FPGA, so you design your golden reference in MATLAB. You design how the ideal system should behave, typically, and then go ahead and do your fixed point design. Because your golden reference will often will be in floating point, right? So do your fixed point, you do your quantization, do you introduce other optimizations that you might need to do, and then compare your outputs against your model or your golden reference, right? And see whether this is according to what you expected, right? So that is how you would kind of go from your specifications back to your integration very quickly with this. Now, suppose we had some analog blocks. So what do we do with those? Like like how do we kind of implement these, right? So again, the idea here is, let me just open up another example here, which we can look at. Yeah. So let's just open up maybe yeah. So this particular block diagram, it's a simple sigma delta ADC. So I can share this with the. So let me see if I can open up uh, the example for this. So which I'll share a link to this right away. So I think I can simply look at. I think I just opened up an example uh, which came to mind, and then yeah. So yeah, so I'll share a link to this maybe towards the end of this. So let's keep going, right? So in this case, so we just saw a digital implementation, right? So now suppose let's look at let's look at your let's look at our analog implementations. Um, so the idea is not to kind of do your circuit design in MATLAB, but essentially try to build a high level model in MATLAB which describes circuit behavior. Okay, so you in this case for a signal delta ADC, you kind of have your signal source. Uh, have say so your low pass filters followed by your gain blocks and your entire uh, integrators, quantizers, and so on, followed by your decimation filters and so on. And then you're looking at uh, creating a high level model which implements this. And then so imagine sort of implementing something like this in uh, code, right? So it would be sort of difficult to do, and especially when it comes to say multi-rate systems and if system complexity increases, then it becomes even more difficult to make uh, to take into account uh, different sort of say keep account of what time uh, others are working at and so on. And in case of analog, you are also looking at uh, you're looking at continuous time simulations, right? So you're looking at uh, so solvers which are there uh, again. So in this case, you have suppose I want to. What you can do is you can go ahead and generate C code from various blocks of this, and then use like wrap it around a system verilog wrapper, and then import it into your uh, Virtuoso or AMS environments. Okay, so again, what can you do is you can look at say creating creating say sub blocks. So something like this. You can go ahead and create a subsystem. Similarly, I'll just go ahead and create a subsystem out of this, as well as maybe just these two. These two, let's keep them like it is. So, and then what you again, the idea is, so how, so I hope everyone gets how simple it was to kind of to build something like this, because all of these blocks are available right away. So you could simply say go to your Simulink uh, continuous blocks, and you have your integrators. Okay, you have your math operations here. So you have all of your operations here, your add blocks and so on, as well as you have your quantizers and sample and hold sort of. So you can look at, say, your so you have your quantizers here. So I can simply say search for so yeah, so you have a basic Simulink discontinuities. Yeah, so you have your quantizer blocks here and so on and so forth, right? So you can simply go ahead and describe your system behavior at a very high level. And then what you can do is, if you go back, simply go to the modeling tab, go to model settings. This should open up this environment again, same as before where we saw the solver settings. If you look at code generation here, you have a bunch of options here. So you can look at, say, you can simply say browse for your target file. And what you can do is you can simply go ahead and say describe what you want to target, right? So in case you want to target, in this case, a system verilog component, so you can go ahead and look at generating system verilog files for this. Okay. The so once you have done that, you can go back to your uh, you can go back to uh, uh, your uh, your design tools for your analog design, and then import them and try to kind of model your system in that fashion, right? So again, I don't have either Cadence or AMS sort of uh, on my system, so unfortunately, I'm not able to kind of demonstrate that. But uh, please go ahead and examine uh, any examples that you want to kind of look at. All right. So I hope uh, this uh, this gives you an so this gave you a sort of introduction to where you can use MATLAB and Simulink, and how you can do your design at a very high level, and then then delve down into details. Right? Yeah. So the idea is, again, let me just I'll just quickly summarize. So you can model your time in this. Uh, you can go ahead and say look at uh, incorporating, say, multiple domains in your model. So right from your digital to analog to different models, you can go ahead and incorporate that, as well as you can look at, say, uh, in case there's some functionality that you don't have, right? So then you can simply write code for doing that. So you can simply import and go ahead and use that. All right. So in this case, this is just describes HDL code generation, but you can go ahead and look at something else as well. So another question is maybe to look at, which you often get is, say, uh, uh, you kind of try to describe this in using high level blocks, right? So can you go ahead and generate uh, so this was using Simulink, but if you are, you can also go ahead and uh, describe this entire system uh, in using physical components. Okay, so those physical components are available in uh, a a library known as Simscape. So in this case, if you look at the Simscape library, there would be an electrical library in here, and you have, say, various circuits, integrated circuits, passive elements, elements for describing sensors, transducers, and so on and so forth. So this is again an example of a to D converter, a delta sigma 1, uh, modeled inside using these physical elements. So again, if you have, even if you build this using these physical elements, you can still go ahead and generate C code and then use this to kind of do uh, your design. Uh, so what I'll do is I'll just uh, quickly open up these two examples. Uh, Sure. So this is one particular example. So what you can do is I'll just share this link with you on the chat, and you can go ahead and utilize this. And the other one, um, uh, let's let me just open up the other one as well and share that link as well. So in this case, you can simply, if you open this up, you can see you would get a option of copy command or open model. So you can simply say copy that particular command, enter it in your MATLAB Online command window, or uh, if you're working with an installed version, you can simply say open, and it should do that. Uh, yeah. So let's see. I think this is all that. Uh, One last thing is, again, uh, since many of you might be new to this, how to kind of start learning this in a structured fashion, right? So if you open up Simulink uh, on the top here, so you have an option called Learn, okay, and on the Learn tab, you would get, say, options of how you can go ahead and there are various courses here which are freely accessible to all of you. So you can do something like a Simulink on-ramp, which is a 2-hour course, a code along sort of course where you build a Simulink model from scratch and try to kind of get the basics. Uh, so Simscape as well as circuit simulation is something that you can go ahead and look at as well. Okay. So let me just go ahead and launch the circuit simulation on ramp. And you can get an idea of what it looks like. So uh, this would open up a window like this, and it would connect to the internet, uh, get try to kind of do this course, and you can try this out. So this would work even on MATLAB Online. Uh, so if you can open up Simulink in MATLAB Online, you will get access to all of these courses as well. So these should be freely available to you. So you want to learn more on your own time, I think please go ahead and try that out. So yeah. Uh, while this opens up, since we are already almost at the end, we have maybe 5 minutes remaining. So please feel free to kind of, if you have any questions whatsoever, please feel free to kind of ask, put them on the chat, or I'll try to answer them the best I can. Yeah, I hope this was useful, and what we talked about was useful, and I was able to kind of give you an idea about a high-level overview of how uh, MATLAB and Simulink can be used in uh, your circuit design for chip design. There are a lot of other applications which we didn't go into, but I think this is a good point to kind of uh, to end at. Yeah. So yeah, please feel free to kind of go ahead. In case you have any questions whatsoever, please feel free to kind of email me here. For some reason, simulation on ramp is taking forever to launch. I'll just go ahead and
Yeah, Praful, while this is launching, I would really like to thank you for your time and all the efforts and preparation that you have put into for coming up this nice workshop for 2 days. And on behalf of IEEE SSCS Daily Chapter, I really thank you for all the good work that you are showing. And I'm sure this would be very beneficial for all the participants. And in case there are further questions, Praful has already shared the contact details, so please feel free to contact him. And we would be having many more sessions like this. We are planning for the benefit of the engineering students and the professionals. Stay tuned for that. So on behalf of IEEE SSCS Daily Chapter, thank you very much for attending this. And thanks once again, Praful,
sure.
for making this happen. Thank you so very much.
Yeah, thank
Yeah,
you. Thank you, Sanjay, for like taking the initiative. You, Rakesh ji, and Sankesh have been great in sort of helping coordinate this. I realize just also, like, at times this might be too introductory at some level for many of the joinees. So please feel free to get back to Sanjay in case there are specific topics that you would want IEEE Solid State Circuit
right.
Society to cover, because without
Yes,
that sort of feedback loop, I think it won't be sort of we'd be looking at topics which we think are
right.
important, but we would really like to kind of learn more from your side. Yeah.
From the audience, of course. Yeah, yeah, indeed. So very rightly said, Praful. We will see. And to all the participants, we will share the recordings on LinkedIn, and you will be able to access it,
Sure.
right? In
Sure.
case you want to refer back. Yeah.
Yeah.
So
Yeah.
with that, I think we can close this session. Thank you once again, and have a good rest of the day. Bye bye.
Bye bye.
Take care.
Thank you. Thanks
Bye.
everyone.
Bye.